Okay, let's get started. Today, we are going to continue our discussion on geometric representations. Last class, we introduced the two most commonly used type of geometric representation in computer graphics, which are implicit representations and explicit representations. We went over some of the trade-offs and the different characteristics of these two different representations. And then for today's lecture, we're going to focus on the most commonly used type of geometric representation in computer graphics, which is polygon meshes. So we are going to introduce what polygon meshes are, why it's so commonly used, and then we are going to go over some of the different data structures that we can use to represent a polygon mesh, and look at some ways that allow us to efficiently represent a polygon mesh on the computer. Okay, so let's start by taking a look at what is a polygon mesh. A polygon mesh is a kind of explicit representation of a shape, where we represent the surface of a shape by using small polygon patches. So one way that we can go about constructing a polygon mesh is to sample a bunch of points on the surface of an object. And then we connect those vertices with edges in order to form little polygon patches. And each one of these little polygons will be an approximation of what the surface of that object looks like over that small patch. And on the right, we have an example of the first polygon mesh that was constructed in computer graphics, which is called the Stanford Bunny. Now, one of the key design decisions that we have to make when constructing a polygon mesh is what polygon should we use to represent the surface patches on our object. For example, we could use triangles to represent the little surface patches in our mesh, and this would then lead us to a triangle mesh, where the surface of the object will be approximated by a bunch of little triangles. But we can pick other polygons as well. For example, we can use quadrilaterals, and this will give us a quad mesh, where the surface patches on the mesh are represented using little quadrilaterals. And we don't have to stop there either. We can really use any polygon we want. We could use a pentagon, a hexagon, an octagon, and so on. So when constructing a polygon mesh, we can use lots of different choices for polygons for representing the surface patches on our mesh. And we don't necessarily have to pick a single polygon to use as well. We can mix and match between different polygons. So even though there are lots of different choices that we can make in terms of the type of polygon that we use for our polygon mesh, in practice, the vast majority of polygon meshes are represented using triangles. So most of the 3D meshes that you see in games and films, chances are they're represented as a triangle mesh. And one of the reasons why triangle meshes are the most common option for polygon meshes is polygon meshes is because it offers a lot of really nice properties. Okay, so what are some advantages of using a triangle mesh? Well, triangles have a really nice characteristic where any complex polygon can be decomposed into a set of triangles. On the right here, we have an example of a fairly complex polygon in the shape of Canada. And even though this is a very complex polygon, we can decompose this complex polygon into a mesh of simpler triangles. So in this case, this shape can be entirely represented by a collection of smaller triangles. And we can take any complex polygon, and we can always decompose it into a simpler collection of triangles. Which means that any non-triangular mesh that we have can always be decomposed back down to a mesh that only contains triangles. So this is a really nice property of triangle meshes. Another very nice characteristic of triangle meshes is that all triangles are guaranteed to be convex. As a little reminder of what convexity means. We say a shape is convex if we can pick 2 points inside a shape. This can be any 2 points we want. And we can draw a line connecting those 2 points. And the line that connects these 2 randomly sampled points will be fully contained within the shape. In the case of a triangle, we can pick any 2 points we want. We can draw a line that connects these 2 points. And that line is guaranteed to be fully contained within the triangle, which means that it's not possible for me to find 2 points and where it's not possible to pick 2 points in a triangle such that the resulting line has some point which is not contained inside the triangle. No question?
Go back to last slide.
Sure.
If that atom polygon
Yep.
is fine, they're overlapping like vertexes, but then on you like they're now.
Right, yeah. So there's some extraneous lines here. So this is not necessarily the best visualization of a mesh, but you can decompose this into a mesh of purely triangles. This diagram might just not be the best illustration of that. Right. So if a shape satisfies this characteristic, we say that this shape is convex. Okay, but triangles are not the only convex shapes. For example, I can take a cube like this. We can pick any 2 points inside this cube, and the resulting line will be fully contained within that cube. So in this case, this cube is also convex. Okay, but cubes are a special example for quadrilateral. And it turns out it's possible to construct a quadrilateral that is not convex. For example, I can take this cube, I can pick one of the vertices, and I can move it towards the interior of the cube. And if I move this vertex far enough, at some point, the quadrilateral is no longer convex. So for example, I can pick this point here, and this other point on the opposite edge, on the opposite corner of the cube. We can draw a line that connects these 2 points, and a segment of this line is now outside of the quadrilateral. So in this case, this particular arrangement of vertices leads us to a non-convex quadrilateral. And it turns out triangles are the only polygon that's guaranteed to be convex, regardless of how we position the vertices. This means that no matter how we place the different vertices of a triangle, we are always going to get a convex shape at the end. And as soon as we get to a polygon that's more complex than the triangle, so anything that has 4 vertices or more will lead to a polygon where it's possible for there to be configurations of vertices that no longer results in a convex polygon. So triangles have this nice convexity guarantee. Any questions about what it means for a shape to be convex? Right. So the reason why we care about whether or not a shape is convex or not is that a lot of the downstream applications that we are going to use meshes for, things like geometry processing and rendering, a lot of those techniques become a lot easier if the shapes themselves are guaranteed to be convex. If, for example, if we use a quad mesh, if some of the quadrilaterals are convex and some of the quadrilaterals are not convex, then when you implement these algorithms, you're going to have to have different cases in your code to handle shapes that are convex and different branches of your code to handle shapes that are not convex. So this increases the complexity of the algorithms, also makes a lot of these implementations a lot less efficient compared to if we only have to handle convex polygons all the time. Yep, question.
Shape convexity, is it guaranteed to also be
No, not quite. So in the case of the cube there, you can have a convex cube that's not necessarily plane though. Wait, hang on. Well, actually, I'm not sure about it. I'm not sure if convexity guarantees flatness, but we're going to talk about flatness next. Okay, but any other questions about convexity? Okay. Right. Okay. Then triangles have a nice guarantee that they're always going to be guaranteed to be convex. Another really nice characteristic of triangles is that they're also guaranteed to be flat in 3D space. So let's take a look at what we mean when we say their shape is flat. In the case of a triangle, I can take any three vertices I want. These vertices can have positions anywhere in 3D space. Given these three vertices, I can connect them with edges to form a triangle. And the resulting triangle will be flat because it can be fully contained along a plane. So I can take those three vertices, I can construct a triangle, and then I can fit a plane to this triangle. And the triangle will be fully contained within the plane, which means that there are no points on the triangle that is off the plane. And when the shape can be fully contained within the plane, we say that this shape is flat. And the nice characteristic of triangles is that I can pick any vertices I want. I can place the vertices anywhere I want. And the triangles that are produced by those three vertices can always be fully contained within the plane. It might not be the same plane, but they can be contained within some plane, which means that all triangles are guaranteed to be flat. And it turns out triangles are the only polygons that are guaranteed to be flat. For example, let's say we take a quadrilateral. I can orient the vertices in a way that's fully contained within the plane. And in this case, this particular quadrilateral is flat. But now if I take one of the vertices, let's say this corner over here, and I move it orthogonal to the plane. So if I move this vertex along the normal direction of the plane, then that single vertex will be off the plane, while the other three vertices are contained within the plane. Which means that it's now impossible to fit a plane that fully contains all four vertices of this quadrilateral. There will always be some point in this quadrilateral that's going to be off the plane. And in this case, we say that this shape is no longer flat because it can't be fully contained within the plane. Okay. Any questions about flat shapes? Okay. So triangles also give us this nice guarantee that whatever triangle we produce is always guaranteed to be flat. And as alluded to in the previous question, one of the reasons why we care about these nice guarantees from triangles is that they make a lot of downstream applications for triangle measures much simpler and much more efficient. When we are implementing different geometry processing algorithms, when we are implementing different rendering algorithms, if we are only working with convex and flat triangles, then this can greatly simplify the algorithms that we need for processing those measures. We only have to design algorithms that work for triangles. And if all of our measures are represented by triangles, then those algorithms will be able to be applied to any mesh that we construct. Another advantage of these nice guarantees from a triangle is that they allow us to really optimize a lot of our code specifically for triangles. So for a lot of rasterization algorithms, for a lot of the rasterization pipelines that are implemented on GPUs, they're very carefully optimized specifically to process triangles. So because we know that we only ever have to focus on triangles when processing meshes, then this allows us to design very efficient algorithms and also hardware to specifically accelerate computation that we have to perform on triangles. So because of all of these nice characteristics of triangle meshes, most of the geometric models that we work with in computer graphics will be represented as a triangle mesh. And for pretty much all the remaining discussion in this class, as well as in the following classes, we are going to by default assume that we are working with triangle meshes. So whenever we see a mesh, we're going to assume that's just represented by triangles. Okay. Any questions about any of this? Okay. So if triangle meshes are our go-to representation for geometric shapes, next, let's take a look at some different ways that we can represent a triangle mesh. So one very simple data structure that we can think of for representing a triangle mesh would be by using something called a triangle soup. Similar to how we represent a point cloud as just a collection of different points in space, we can represent a triangle soup as just a bunch of triangles. Okay. So on the right here, we have a very simple mesh that consists of two triangles formed by four different vertices. So we have a blue triangle on the bottom and a green triangle on top. And so we can represent this mesh as just a collection of two triangles. And we can just make a list that explicitly stores the two triangles that represent our mesh. So in this case, we have a triangle. The first triangle we have is the green triangle on top. And this is represented by vertex 0, vertex 1, and vertex 2. So we can then store the three vertices that form the green triangle as an entry in our list of triangles. Then we have a second blue triangle on the bottom that's formed by vertex 0, vertex 3, and vertex 1. And so we can just store a second triplet of vertices that form the second triangle. So triangle soup is just one big list of all the vertices that form every triangle in our mesh. So in this particular list, every three vertices will correspond to one of the triangles in our mesh. And we can just directly store all of the triangles that are contained within our mesh in this one big list. So this is similar to the point cloud example, where we represent our point cloud as one big list of points. In the case of the triangle soup data structure, we represent the triangle mesh as just one big list of triangles. Okay, so very simple representation. Any questions about this? Okay. This is a very simple way of representing a triangle, but it's also a very inefficient way of representing a mesh. One of the drawbacks with this triangle soup representation is that there's a lot of repeated data that we have to store over and over again in this data structure. In our original mesh, it only contains four different vertices. But because some of the vertices are shared by multiple triangles, we end up having to store a single vertex multiple times. So in this case, vertex 0 and vertex 1 are shared by both the green triangle and the blue triangle. And in our triangle soup data structure, we end up having to store each of those vertices twice, once for every triangle that shares that vertex. Now, in this simple example, this doesn't seem that bad. We just repeat the vertices twice. But in a complex mesh where a particular vertex might be connected to tens or maybe even hundreds of triangles, then we might have to repeat the same vertex hundreds of times in our mesh. And that's very inefficient. Another drawback with this simple triangle soup data structure is that common mesh operations are very inefficient with this particular data structure. So common mesh operations would be something like, let's say we want to find all the triangles that share a particular vertex. if we want to do that using this triangle soup data structure, then we have to enumerate over the entire list of triangles and check which triangles are connected to a particular vertex. So if we have a mesh that's 1,000,000 triangles, then every time we perform a query to try to find the triangle that's connected to a particular vertex, we have to enumerate all 1,000,000 triangles. That's incredibly inefficient. And for a lot of geometric processing algorithms, we might have to perform a lot of these queries hundreds of thousands of times per operation. And so using this simple triangle soup data structure can just quickly become very inefficient. Okay. So this triangle soup data structure is very inefficient, both in terms of storage as well as in terms of processing. Okay. So while this is a very simple data structure, in practice, we will often use more sophisticated data structures that tries to improve some of these inefficiencies of the triangle soup data structure. But I guess before we move on to the next data structure, any final questions about this? Okay. Then let's take a look at how we can make this triangle soup data structure a little bit more efficient. So first, we're going to take a look at how we can improve the storage and efficiencies of the triangle soup. So if a vertex is shared by multiple triangles, we want to avoid having to repeatedly store the same vertex multiple times. Now, one way that we can do this is by introducing an extra layer of interaction into the data structure. So first, we're going to have a big list that stores the vertices in our mesh. So this is just one big list that stores every single vertex contained in the mesh only once. And you can think of this vertex list as just the point cloud data structure that we started with in the previous lecture. So this is just one big list of points that's in our mesh. And this vertex list is going to store the vertices, the positions of the vertices of the mesh, and it can also store other characteristics as well. But the key here is that every piece of information of a particular vertex will only be stored once in this big list. Now, next, we're then going to connect the vertices in this vertex list into triangles by using a separate face list. This face list is going to represent the triangles in our mesh, where every entry in this face list is going to store the indices of the vertices that form each triangle. For this simple mesh here that only contains 2 triangles, our face list only contains 2 entries as well. The first entry corresponds to the first triangle, the green triangle on top. And it's going to store vertex 0, vertex 1, and vertex 2. So it's just going to store 3 indices that tells us which vertices are used to form the first triangle. And similarly, the second triangle, the blue triangle, is formed by vertex 0, vertex 3, and vertex 1. And so the second entry in our face list just stores those 3 values that specifies the vertices for the second triangle. And if we have more triangles in our mesh, then we'll just store a longer list of indices in the face list. And the efficiency improvement that we get from this vertex list and face list data structure is that we now only have to store a vertex once. We never have to store the same vertex multiple times. And all we have to do is that to construct a triangle, we just have to store the indices of the vertices that form that particular triangle. But that's just a single number, and repeating that multiple times is not such a big deal. So this then greatly reduces the amount of duplicate data that we have to store for the vertices of the triangle. And so this improves the storage for our triangle mesh quite a bit, especially as the mesh becomes more and more complex. But the drawback with this vertexless, with this faceless data structure is that mesh operations are still fairly inefficient. So again, let's say we want to find all the triangles that share particular vertex. So let's say I want to find all the triangles that share vertex 0. If we want to perform that operation with this faceless data structure, then we still have to enumerate over all of the triangles in our list to find all the triangles that are connected to a specific vertex. And for a complex mesh, this can still be very inefficient. So while this particular data structure improves on the storage efficiency of our triangle mesh, mesh operations are still fairly inefficient using this data structure. Okay. So before we look at a more sophisticated data structure that can make these mesh operations more efficient, any questions about this faceless data structure? For this particular data structure, the ordering of the triangles don't matter, but the ordering of the vertices within the triangle does matter. By convention, we typically follow the right-hand rule, where we store vertices counterclockwise around the normal of the triangle. But this is just a convention. You can go the opposite direction as well. But I think the important part is to pick a convention and be consistent with it. So in practice, people usually just follow the line. Any other questions? Okay. Then next, let's take a look at how we can design a data structure that will make common mesh operations more efficient. To design a more efficient data structure, we are first going to take a look at some useful concepts we're going to take a look at some useful concepts. And kind of the concept that this data structure is going to take advantage of is to leverage the difference between the topology of a mesh and the geometry of a mesh. Okay. So when we talk about the topology of a mesh, this refers to the local structure of a mesh, which describes how the different vertices are connected to each other. So the topology of a mesh is mainly focused on which vertex is connected to which other vertex. But the topology of a mesh doesn't really care about the global structure of the mesh. So the global structure of the mesh is defined by the geometry of the mesh. And this is represented by both the topology, how the vertices are connected to each other, as well as the actual coordinates of the vertices themselves. So when we talk about the geometry of a mesh, we care not only about how the vertices are connected, but the actual 3D coordinates of the vertices as well. So to see this difference between topology and geometry, let's take a look at some different meshes. So here we have two meshes where one mesh is just a rotated version of the other mesh. So the second mesh is we just took the first mesh and we just rotated all the vertices by 90 degrees. Now in this case, we can say that the two meshes have the same topology. Vertex 0 is still connected to vertex 1 and vertex 2. Vertex 3 is still connected to vertex 1 and vertex 0. So the local structure, the connectivity between the vertices are the same for both of these meshes. So they have the same topology, but the geometry is different because the 3D coordinates of the meshes, of the vertices themselves, are not the same. So in this example, we can say that the two meshes have the same topology, but they have different geometry. So next, let's take a look at a different pair of meshes. In this case, we have two different meshes, but the second mesh, in the second mesh, we have removed one of the edges of the mesh that connects vertex 0 to vertex 1, and we introduce a second edge connecting vertex 2 to vertex 3. So in this case, the coordinates of the vertices are the same, the positions of the vertices have not changed, but the connectivity of the vertices have changed. So in this case, we can say that these two meshes that have different topologies. And because they have different topologies, that also means that the geometry is different. Because the geometry depends both on topology, both the local structure, as well as the global structure of the vertices. Okay, right. So in this case, we have a mesh. We have two meshes that have a different topology and different geometry. Now, the key insight that we can leverage to make mesh operations more efficient is that many of the common mesh operations that we want to perform, they rely only on the topology of the mesh, and they don't really care about the geometry of the mesh. So a lot of the common mesh operations that we want to perform, they only care about how the vertices are connected to each other, and they don't really care so much about the actual positions of the vertices themselves. And we can leverage this characteristic to find a much more efficient data structure for mesh processing. Okay. Any questions about this distinction? Yep.
Both examples have different geometry.
Yep, that's right. So both examples have different geometries, but the example on the left has the same topology. Any other questions? Okay. Now let's take a look at how we can leverage this characteristic to design a more efficient data structure. So one widely used data structure for geometric representation is half-edge data. It's the half-edge data structure. And the idea with the half-edge data structure is that we can explicitly encode the topology, the connectivity of a mesh, by using a kind of doubly linked list. So the half-edge data structure you can think of as just one big linked list that stores pointers to different entities in a mesh that are connected to each other. Now, the key entity in the half-edge data structure is something called a half-edge. And these form the nodes that we use to connect all the different parts of the mesh together. So let's define what a half-edge is first. A half-edge is formed by taking any edge in our mesh and splitting it into two halves. So for example, let's take a look at the horizontal edge that's shared by both the green triangle and the blue triangle. We can take this edge and we can split this edge into two half edges, where you have a top half edge that belongs to the green triangle, and then a bottom half edge that belongs to the blue triangle. So for any edge in our mesh, we can construct two half edges by splitting that edge in two. And in the half edge data structure, the half edge is the key data structure that we are going to use to form the linked list that stores the topological information of the mesh. So this is an example of a simple pseudocode for how we would represent a half edge. So a half edge contains a bunch of pointers to other entities in the mesh. Now, in addition to the half edge, we might also introduce some other data structures to represent the vertices, the edges, and the faces in our mesh. So let's walk through how these different data structures work. So first, let's take this half edge as our example. So this half edge is constructed by splitting the horizontal edge in two, and this half edge is going to belong to the green triangle on top. Now, this half edge is going to store a bunch of pointers to other entities in this mesh. So first, this half edge is going to contain a pair pointer that corresponds to the sibling half edge that shares the same edge as our current half edge. So the top half edge shares the horizontal edge with the bottom half edge that belongs to the blue triangle. And we'll refer to this sibling half edge as the pair half edge. Okay, next, the half edge is going to store a pointer to the next half edge that belongs to the same triangle as our current half edge. As we mentioned before, we order the vertices counterclockwise around the normal of a triangle. So the horizontal half edge at the bottom of the green triangle is going to be connected to this next half edge in the triangle. So the horizontal half edge is going to store a pointer to this next half edge that belongs to the same green triangle. And then it's also going to store a pointer to the previous half edge that also shares the same triangle. So each half edge is going to store pointers to other half edges that form a triangle with our current half edge. In addition to pointers to other half edges that a particular half edge is connected to, we are also going to store pointers to other entities that the half edge is connected to as well. So we're going to have a pointer that stores the triangle, the face that lies on the left side of this half edge. Again, because we order the edges counterclockwise around the triangle that half edge belongs to is always going to lie on the left side of the half edge. So in this case, the horizontal half edge is going to belong to the green triangle top. So it's going to store a pointer to the triangle that that particular half edge belongs to. The half edge will also store pointer to the origin, the vertex at which the triangle originated from. So again, because the edges are ordered counterclockwise, the horizontal half edge is going to store a pointer to the left vertex. And then finally, each half edge is going to store a pointer to the edge that it belongs to. So for this horizontal half edge, it's going to store a pointer to the horizontal edge that it was constructed from. Okay. So the half edge data structure contains a bunch of pointers to other half edges and other vertices, faces, and edges that half edge is connected to. And similarly, for the other data structures, for the vertices, for the edges and faces, they're also going to store pointers. But for these other data structures, they only store a pointer to one of the half edges that are connected to that particular entity of the mesh. So for example, in the case of a vertex, a single vertex can be connected to multiple half edges, since we might have many edges that are connected to a single vertex. But one of the really nice characteristics of a half edge data structure is that instead of having to store a list of all the half edges that are connected to a particular vertex, we only have to store a pointer to one of the half edges that are connected to any particular vertex. And by leveraging all the pointers that are stored in the half edge data structure, we can use that single pointer to one half edge to retrieve all of the edges that are all of the half edges that are connected to a particular vertex. So we only have to store data structures that have a constant size. We don't have to store a variable length list depending on how many edges are connected to a particular vertex. Now, similarly, every single edge is going to store a pointer to one of the half edges that belong to that edge. So every single edge can be split into two half edges, but instead of storing pointers to two half edges, we only have to store a pointer to one of the half edges, and we can use the linked list to recover the other half edge. Similarly for faces, so every triangle can be constructed by using three half edges. But instead of storing 3 half edges, we only have to store a single half edge. And again, we can then follow the pointers to retrieve the other 2 half edges very efficiently. And we're going to go through some examples of how we use this linked list data structure to retrieve different elements of a mesh. But kind of one of the key characteristics of this half-edge data structure is that every data structure has a constant size. We don't have to store variable length lists. But by leveraging the pointers in the half-edge data structure, we can very easily retrieve other elements of the mesh that's connected to a particular vertex or face or an edge. Okay. I think this might be a good point to wrap up for this lecture. We're going to go through some examples in the next lecture of how we leverage this half-edge data structure for performing mesh operations. But before we wrap up for today, any questions about this? Yep.
The half edge, that enough information for each triangle?
Yeah. For every triangle, we only have to store pointer for one of the half edges, and then we can use the next and previous pointers in the half edge to retrieve the other 2 edges. So we don't have to explicitly store all 3 edges for a triangle. Any other questions? Okay. If not, then we'll wrap this up on Friday. See you.